forward some queries for you. Okay, we expect honest answers from the students. Okay, so let's have this query. Do you revise the contents of lecture at home? Honest answers, please. Does not harm you anyway. Yes, always. I never see the contents of lecture at home. Sometimes I have a look at videos or contents. I don't care anything. I shall read when MST or final exam will come. Okay, will be near. Okay, no problem. Yes, please answer. 7 students have not replied, please. Yes. Abhay, you have not replied. Akepam, Neha, Ravinder Kumar Thakur, you have not replied. Please reply. Okay, yes. So I'm going to share responses with you guys. Okay, so you can see that most of the students are saying sometime I will look at the videos or contents. Okay, I shall read when MST or final exam will come. Okay, 4 students are saying yes, always. 8 students are saying that it's good. Okay, anyway, we are having this information. So let's have a discussion about our lectures which we have started, the FTIR. And what we have seen that I told you that this is very important to understand this FTIR because most of the time students are not aware from where the spectra is coming. So let's have a quick look what we have done so far. Or yes, okay. So let's have that information for us. I'm just putting up the information for you. So if you recall in our Saturday's lecture, we have started this the FTIR spectra and how does it work that we have seen. Okay, and if you have a look at it, then we can have a direct comparison of it. That how does it work and what are the contents, main contents which we were looking at. Okay, so let me share screen with you guys so that we can have this information. So I'm sharing screen with you. Okay, now we are on screen sharing, and if you look at this one, this lecture, what we have done that we try to emphasize here that what is the meaning of the Michelson interferometer. Basically, what we have done that we were trying to understand this FTIR spectrometer, and I told you that the major component of the FTIR spectrometer is a Michelson interferometer. And what are the contents of the Michelson interferometer that we have discussed, no? And how this Michelson interferometer works? What are the requirements in that case that we have to see, no? So let's just a minute. Okay, so what we have done that we were trying to understand what is the meaning of this. We have a source and a beam splitter. Most straightforward contribution of this Michelson interferometer. And after that, what we have that we have introduced a compensating plate in order to compensate the path difference between the two mirrors. So basically the moving mirror and this stationary mirror, the difference between the optical path lengths. So remember that I am using word optical path length. That is very, very important. This is related to the speed of light when it travels from this fixed mirror to this mirror in this case. Okay, this beam splitter to fixed mirror, and then you have from this beam splitter to the stationary mirror in this case. So that path length that will be termed as the phase that retardation in this case. So we have also defined that what is the meaning of this retardation. So here what we have done that we have tried to understand that what is the meaning of this beam splitter, and then this was an important curve, no? So what we were trying to understand here, this one. Okay? So you would have here what you are trying to do. You are trying to move it. Let's say that on this position. Okay. So what is the moral of the story? Instead of discussing that in the parts, we would like to discuss what is the moral of the story. So that we have to come across. So what is the moral of the story in this case? We have to get into that details which are there. So moral of the story is that the you would have the maxima and minima which will be detected by the detector, and these maxima and minima that will be corresponding. If you have the lambda, if it is half in integral multiple, let's see that. Okay, if you look into this details, then you will see that if it is the half integral multiple or integral multiple of the wavelengths, in that case you would have maxima or minima. Okay, that information you would have here. Okay? If you look at this, then what you have, so you will have this information about this lambda by 2 when the retardation. What is retardation? That we have already written here. Okay, so it was the value which we were having. Okay? So if you look into the details of this retardation, so we have this value. Okay, so what it is? It is the retardation delta that will be equal to what? It will be equal to 2 into OM minus OS. Okay. What is OM? OM is this the optical distance between the beam splitter, this first beam splitter, and the movable mirror. What is OS? OS is the distance between the beam splitter and the stationary mirror, this one in this case. Okay, so that we have seen in this case. And why we are using this 2? Because you are having this 2 function, because the ray of light will go to the mirror M and it will also come. So it is the path length will be traveled by the ray of light twice. Okay, it will be 2 times. Okay, so that's the reason we have multiplied this one. Okay, what we have seen that if it is the half integral multiple, in that case you will get destructive interference. If it is the integral multiple, in that case you will get the constructive interference in this case. And ultimately what we have also seen that your detector will detect all the things according to this pattern which is going on. Okay, we have inserted the samples so that every sample would have a spectral fingerprint which will give you the details of the sample in this case, no? So that how it works, what are the details which we need to understand in this case, that is very, very important. That this was the story which we have concluded in one of our lectures, and I think the interference fringes we were talking about. Okay? If you have 2 beams of light, in that case what will happen, that you would have the fringe pattern, okay, which you are talking about. Okay? What you are talking about, so if you have 2 beams of light which are interfering, if these are the coherent beams, in that case what you will have the interference pattern which will be generated in this case, and the type of the interference pattern, whether it will be a circular interference fringes or rings will be formed, that depends on the type of the interference, the angle between these 2 lights which are coming in this case. No? So what essentially, if you look into the elementary books of Michelson interferometer, they convert this setup into that setup where both of the beam, the observer who is sitting in front of the detector, he will see that these beam, both of the beams, they are coming parallel to him, and then you can see that they are overlapping in this case, and then geometrical optics can be applied in order to see that what kind of the interference fringes will be there. Okay, we would have circular fringes in this case, or we would have zebra-like fringes, or some the straight fringes. That depends on the type of the interference which you have. Overall, our idea would be the setup would be well aligned if you have the circular fringes in this case. So as far as the sources are concerned and the other stuff, in our next lecture, what we have done, that we came across this problem of that how does a spectrometer works. No? If you look into this discussion, what we have done, Okay, with this, in this lecture, what we have done, we have started with the details of the sample which we have. First of all, we would like to confirm that what is the meaning of the Fourier series. And we have written this function fx is equal to this n is equal to 0 to infinity sigma. Then you have an sine n omega x. Omega is the frequency. Bn and an are constant. N is an integer. So n value of n starts from 0, 1, 2, 3, 4, okay, so on. So what you would have that we were trying to understand with this one. The physical meaning of the Fourier series is that if you would have higher number of the terms, in that case it will increase the accuracy of the fit. What we have done that we have tried to understand this with the help of this diagram which is there. Okay, so with the help of this diagram we were trying to understand this, and we were trying to say that if you have higher number of the this n value is high, in that case you would have better fit. So for example, when you have 0, 1, you are having this red line fit, but on the other hand, when you have 0, 1, 2, 3, 4, in that case you have blue line fit, which is converting your fit into a better better fit over this value of the fx. Okay. Then after that, we have seen that what will happen in this case. This is important. No? What are the fundamentals of the IR spectroscopy? What is IR? These are the infrared radiations. Where they lie in the spectrum, if you look into the spectrum of the infrared radiations, then after the visible radiation, let's say that if you can take the region like this, for example, if you are here somewhere, let's say that this is the range of the, let's say that we can take this one. So let's represent this one with the help of this one. Okay. So what we are trying to do here, we have this region. Let's say that here we have a spectral window which is corresponding to the 400 to 700. Okay. So here you would have all the colors. Okay. What type of the colors you would have? Let's say you would have the wavelengths from 400 nanometer to 700 nanometer. If there is any message from any student. Okay. So if you look into the details of this setup, then what you would have here, you would have the somewhere you would have this okay, blue color, and here you would have this red color. Okay. And in between you would have all the colors with your colors. And after that, if you go in this direction, you will be in the region of infrared. Okay, you will say that this is the infrared region. Okay, above 700 nanometer. And if you go to the other direction, so let me give that. Okay, so it would be like your in this direction. If you are going, in that case you would have the ultraviolet region. Okay, so what you would have, this is the ultraviolet region. Both of these ultraviolet region and IR regions, they are very near to the visible region, which is sensitive to our eye. On the other hand, the IR radiation, for example, if you are starting from the exact location of this, you can say 0.7 micrometer to, let's say, like 50 micrometer. It goes, and sometimes it is difficult to differentiate even that where does it go. Okay, but let's say that 50 micrometer. Okay, this is 7 micrometer to 50 micrometer. This is the region which you are talking about in this case. The idea is that here, if you look at the semiconductor materials, so if you convert this energy of the visible photon into the, let's say that if I am converting 400, so 400 nanometer, convert 400 nanometer into electron volt, okay, corresponding energy. So it will come out to be, let's say that if you have 1214 divided by 400, so how much it would be, that the value you can calculate, okay. You would have here 3.1, okay. So that will be equal to 3.1, okay? It is 3.1 electron volt. So if you are in somewhere near this region, which I am pointing out here, okay. If you are somewhere near this region, okay, so like this one, okay, so like this 400 nanometer, in that case what you are trying to do, you are having the energy of the photon is equal to 3.1 electron volt. So what it can do, that if you look into the band gap of certain semiconductor materials, in that case you will, what you can do, that here you can excite some band gap. With the visible radiation you can excite the electronic energy levels. If you have energy band gap, or if you have wide band gap, in that case you can excite that with the visible radiation or with the help of these ultraviolet radiation, okay. If you have more towards the insulators, then you can excite that with the ultraviolet radiation. What will happen if you are going in the opposite direction, okay? Now you are here, okay, somewhere here, okay? Now what you will do, 700 nanometer. Now the separation, if you calculate, let's say that I can calculate that also for you guys, that what will happen, uh, what will be happening in this case, if you would have, let's say that I'm just taking care of this. So let's say that 1 micrometer, okay? If you have 1 micrometer or 1000 nanometer, then if you are converting 1000 nanometer, 1000 nanometer, which is IR, if you are converting that, in that case what will happen, the energy that will come out to be 1.24 electron volt, okay. And if I am going beyond this, okay, if you are going 50 micrometer, okay, in that case what will happen, this energy level difference, the energy of the photon, that goes decreasing and decreasing, okay. What will happen, so at one stage will be remaining there, okay, when it will be few electron volt, like let's say 0.01 electron volt. And even when you go far infrared radiation, it will go into milli electron volt in that case, okay. Milli electron volt, the energy. Why I am telling you this, because now here you are going towards the semiconductor, when you are going towards this this region, okay, which is the region which is 400 nanometer or below 400 nanometer in this case. But on the other hand, when you are going to IR radiation, you are trying to excite the levels which are the vibrational levels or rotation level. Basically, in order to excite the vibrational and rotational level of the molecules, you need to have very small energy. That small energy which you can have with the help of the IR radiation. And in the chemistry, this is very important, as well as in physics also. So because most of the students, they deal with the material science, it is very important to have this IR radiation in this case. What we have done, that we have taken an example, and what we are trying to say that, okay, we have this formaldehyde molecule. You can take any example, like you can also take the water molecule, you can also take any other molecule. So what you have done, that we have just approximated it like like a dumbbell, okay. So there are two balls, which are what they can do when they absorb energy, then they can either stretching vibrations will be there, okay. Stretching vibrations can be there, okay. The second option can be there, okay, but it can be do. There are another options, okay. You would have, they can come like this, okay, when they absorb, okay. It will be fixed energy which they can absorb, fixed frequency. And we have taken an example of 2 hertz in this case, that this is the energy which is the vibrational energy of the dumbbell shaped molecule which is there in this case, okay. What we were trying to do, that when we are throwing these energies, okay, if you look, that is somehow interesting, okay, very interesting. So what we are trying to say in this case here, the entire rate is not one molecule, hertz or 2 hertz, depending that in this case you would have along y-axis. So right now what we are trying to understand here, that here you have a source, and source is giving you the infrared radiations. How the energy is being absorbed by the molecule. So when we are shining an energy or frequency equal to 1 hertz, then what will happen? Because the vibrational frequency of this molecule does not match with the 1 hertz, it will match with 2 hertz. What will happen, that the light which you have thrown on the molecule, that will be transmitted as such, and you will get 100% transmission in this case. So you will see that, okay, there will be no loss of the light which will be there. Okay. On the other hand, when you would have 2 hertz, in that case, what you are trying to get, you are getting 0% of the light, because all of the light is being absorbed by the molecule which is under consideration in this case. What will happen, that in this case you would have all the details which will be understood with the help of this detector. And then what we have done, that we have also plotted this graph. If you look into the details, we tried that, okay, at when you have 1 hertz, then you have 100% transmission, because no energy is absorbed, frequency is not absorbed, because it does not match with the frequency of the vibration of the molecule. No? So this often happens with the students also. For example, what type of the friends you would have, okay? What type of friends you would have, you will try to look. For example, some of the students, they will be laborious, they will go for study, they will find the friends those who are good in studies, and those who would like to go outside, okay, most of the time they are interested to go outside, look at cinema, or if they have some other interest. Nowadays cinema has been reduced due to the lockdown, as well as due to the internet traffic which is coming over there. What will happen, that this will be like your resonance, no? Resonance of thoughts. Okay. Another example of thoughts resonance is like when you are having some dance party. If there is some DJ and music is going in the loud voice, then sometimes you cannot stop yourself dancing. Why? Because your internal frequency plus DJ frequency, that matches, and then you start oscillation. Okay, so that dancing is an oscillation in that case. Same is the thing here. Okay, when you have matching of the two frequencies, one is the source frequency, okay, and the second one is the frequency of the molecule at which it vibrates. In that case, you would have this this peak which is coming down over there, okay, and then we will get the spectrum. This is the thing which we were trying to understand with the help of the FTIR spectrometer. But actual spectrum is not like this, no? Because we need to, there will be not one molecule frequencies, okay, there will be many frequencies which are absorbed or partially absorbed in this case. So your final spectrum, that will look like, if you have look at that spectrum, I think we have discussed that somewhere, yeah, like this one. Along x-axis you would have the wave number, and along y-axis you would have the transmission, and you will get all the information from here. Now what the scientists have done, that for each of the peak, like that, if you have a carbon, this okay. So let's say that for example, if you have the bonds like, if you have the bonds like C double O bond, if you have any bond like HO bond, if you have any bond like CO bond, if you have any bond like anything, okay, Okay, so all these bonds, they would have their fixed frequency at which they can vibrate and they can absorb energy. Okay, and you can, what you would have, that for each bond you can identify the material. Okay, you can identify, for example, if you are looking at this peak, you are looking at this peak, you are looking at this peak, so each of the peaks in this spectra, that will correspond to a particular value of the bond. Okay, that will be, let's say that you can identify this is located at this frequency. Okay, let's say that 500 centimeter inverse. In that case, you can say that, okay, this is the bond COO bond. Okay, and then you would have this frequency which is H dash O. So for all of these, we would have defined these peaks in this case, and then we can identify that whether what is the composition of our material, which material is present, and what is being done with the material in this case. Okay, that is the thing which we have seen in this case. Next important point is that here, let's have an example. What I would like to say with the help of this simple, I hope that I have enough. This is a piece of cardboard, or this is just a notebook, okay, which I'm talking about. So if you look into this notebook, then what will happen in this case, that I have this notebook, and if I shine, this is the small laser pointer which I often take into account. And laser pointer is important in this case because we are having the source to align our setup with the help of the laser pointer. So what we are trying to do in this case, that I have shined. Okay, you can see this is the light which is there. Can I see the light on the other side of this notebook? Can I see that light? If I shine it here, can I see the light here? No. Answer will be no. I cannot. How I cannot? Because this piece of paper or this notebook will block the incident radiation, which are the visible radiations in this case. Okay? Which are the visible radiation. On the other hand, if you look into the IR radiation, now, for example, if I have a source which is the IR radiation source, when if you have far infrared radiation source, in that case, what will happen? This can go, and you can also see that on the other side of the paper or the cardboard. Okay, so the infrared radiations, they have different physics compared to the visible radiation. They can penetrate through the materials which the visible light cannot. So that is the advantage in this case. But at least what will happen in that case, it will also invite some challenges. You would have this source. If you have a source which is the visible source in this case, everything goes easy. But it is IR source in this case, so your beam splitter, your detector, everything will be changed in this case. Okay, so everything will be changed in this case. And let's have a small discussion about the type of the beam splitter and the sources which we can use in the case of this the IR spectrometer. Okay, FTIR spectrometer. Let's have a look at this. So what I'm going to do, I'm going to divide a discussion into some parts here. Okay, here, and then we would also like to divide it in three portions. And here we would also have this information about this. And here I am writing like your sources. Okay, sources. And here I will write the beam splitter. Okay? This type of the splitter you need to have. beam splitter. Beam splitter. And here I would like to write about the detector. Which type of detector will be good in this case? Okay? So then I would like to divide it in the parts here. The first part would be the near infrared region. Okay? Near infrared region. The second part of ours will be the mid infrared region. Okay? What I am saying here, it is near IR. Okay? Near IR. Okay, and here I would write mid IR. Mid IR. And here I will write about far IR. Okay? Far IR. So near IR means that we are talking about 0.7 to 2.5 micrometer. Okay, and here we are talking about, let's say, 2.5 micrometer to 25 micrometer. 25 micrometer. And here we are talking like greater than 50 micrometer. And we have a window over there which is between 25 micrometer to 50 micrometer. So we will, any type of the source may work between them, but the sensitivity that will go high. Oh, I have done something wrong. Wrong in the sense my table is short, so I would like to make it better. So here we would have beam splitter, and then from here I can divide it into parts. Here we have lambda, the wavelength. Okay, and then here we would have this information about the source. Okay, so here we can have source, and in this region we can have our source. Here we have beam splitter, and here we would have the detector. Okay, so let's have one by one. Okay. So we can have all the information from here. Here we have this the tungsten halogen lamp. Okay? Halogen lamp. And in this region we would have silicon carbide. Okay, heated up to, okay, heated up to 1200 Kelvin. And here you would have mercury discharge lamp. Okay? Mercury discharge lamp. Okay? And here you would have calcium fluoride, IR, and here you would have polymer film. Okay? And here you can have any detector which is like gallium arsenide, uncooled one, gallium arsenide, and then we can also have this DTGS. Okay, and here you can have the pyroelectric detector, pyroelectric detector, and here you can also have MCT, no? And then here you would have bolometer. Bolometer. Okay? So let's have a quick look what we are trying to do in this case. Okay. So what we would like the different sources. Okay, because if you need to have near IR source, then you would have tungsten halogen lamp. Okay, it will give you this light which is from 0.7 to 2.5 micrometer. In the second case, silicon carbide element heated up to 1200 Kelvin, that will give you IR. Okay? And in the last one, you would have mercury discharge lamp, which can give you above 50 micrometer. And in between, you can also have some of the lines which are there. Okay. And here you have beam splitter calcium fluoride in the rear IR. In the mid IR, you would have potassium bromide, and here you would have polymer films in this case. No? And if you look at the detector, then you would have gallium arsenide and DTGS. What is DTGS? It is the we should write this full form. So what is DTGS? Okay? It is deuterated triglycine sulfate. Okay? And then MCT is mercury cadmium telluride. Okay? What is MCT? MCT is mercury telluride, mercury cadmium telluride. Okay? Cadmium telluride. Okay? Basically, all of these detectors, they are sensitive to the IR radiation because these are the heat radiations. In this case, no. This is the things which we have to take into care. And there are also like cesium iodide, which is there, and yeah, these are sensitive in the region like 20 micrometer, where you would have this one. Any questions? Please don't hesitate to ask me questions. Any questions? Any questions? Students have left. Some students have left. Many students have left. Do not hesitate to ask me any questions. You can. I would like to enable your voice. If you have any query, please don't hesitate to ask me. Any query?